Hello everybody, welcome back to my basement. I am here today to record a lecture that goes with example 6C, modeling change over time using truly exponential models. I only know how to do this in SAS NLMix, and so that is the only software that is featured in this example. However, I know for a fact that other people have figured out how to do these sorts of models using other programs, including Stata and R. So just have to ask the Google about how one can write their own versions of models to be estimated using likelihood estimation within those programs. So to begin with, I wanted to describe how to estimate models that are already familiar to us that would have been estimable in mixed using NLMix, just to describe how this package differs from a traditional approach to multi-level models. So this example features the same data that we have been playing with in the lectures and examples thus far. I have 6 sessions of practice in a set of older adults to a measure of simple processing speed, so the outcome is still response time in milliseconds. So I'm reading in the same data as usual. The only variables that I need to create for this example are the session dummy codes that will be used to test absolute fit of the fixed effects with respect to time in the model for the means. Otherwise, all of the variables are going to be created within the NLMix package. So to begin with, I wanted to show you what it would look like to estimate an empty means random intercept model using SAS NLMix instead of mixed. So the basic model looks like this. We've seen this several times up to this point. We have a fixed intercept. We have we have a typo. We have a missing random intercept in this, so let me add that while I'm thinking of it. This is math type, by the way, one of the equation editors that I use. There we go, that looks much better. We have a fixed intercept, a random intercept, and we have a residual. And so this is what the code would look like to estimate this model for our example data, where the empty part is right here. We don't have anything in any fixed effects in the model for the means. We do have a random intercept. So proc NLMix then to estimate this same empty means random intercept model looks like this. It looks very different. There's a lot more code in here because this routine allows us to estimate whatever model we feel like. So this is where your ability to write out a model equation, determine what parameters need to be estimated, this is where it's really going to come in handy. So we have proc NLMix is the procedure in this set of examples. I have some notes here about the technical side of estimation. For these models, this doesn't matter quite as much, although it does matter in some different kinds of models in this where we're not using a conditionally normal distribution. That's where these things really start to make a difference. The key idea here is that in each of these models, we have to name and define all parameters to be estimated. So the 3 parameters to be estimated in the empty model are defined on the parm statement right here. So the letters here to the left of the equal sign, these are names that you make up. So they have to obey typical naming conventions. They can't start with a number, they can't have special characters, but other than that, you can name them however you want. So I've developed a convention in naming these where I have an F in front of anything that's going to be a fixed effect, and I have var for anything that is going to be a random effect variance. So I have a fixed intercept is what that's going to mean, a variance of U0, so that's my random intercept variance, and a variance of the level 1e residuals. The numbers in here are starting values. These came from the empty means model that I estimated in mixed. So a good question that I've received in the past is if you don't know how to estimate the model in a different package, how do you get starting values? And normally I provide a glib response like, well, God. But I will show you in this example how one goes about the process of getting decent starting values in a sequential fashion. So in this case, I'm kind of cheating because I know what the answers are already. If you don't know what a starting value should be, you can just put 0. So then I am defining how these parameters are used in the model equations. So I have a level 2 equation here with a BOI placeholder equals my fixed intercept plus my random intercept. Some extra spaces in here. So that corresponds to this level 2 equation right here directly. And then I have a level 1 equation without the E residual. So at this point, other than the E residual, the only thing that's in the level 1 equation is this beta 0I placeholder. So that's what I have here. The level 1 residual shows up down here. So the model statement requires you to list your dependent variable and to give it a distribution. So I am saying that the distribution of response time is conditionally normal with a mean of whatever is predicted by the model. So pred y is a placeholder for the combination of fixed and random effects that are going to go into each person's predicted outcome. After controlling for the fixed and random effects for each person, then we have the variance of the E residuals as the leftover level 1 variance. So E variance shows up here, and U variance shows up on the next line. So just like in mixed, we have a random statement. I have to list which parameters are going to be randomly varying and what their distribution is. So the random intercept I have named in here U0I, so it's included up here, is going to be normally distributed with a mean of 0, that is true for all random effects, and a variance of this thing right here. So this is going to be my random intercept variance of the U0I's, and that way all 3 parameters then are in the model. So fint shows up here, var U0 is the variance of the U0I's, and var E shows up here in the model line. So all of those match. One nice thing about NLMix is that you can do linear combinations of not only fixed effects, but of any parameter in the model. So I'm asking it to estimate an intraclass correlation, which is defined as the random intercept variance over the total variance given by the sum of the random intercept variance and the residual variance. So there is no G matrix, there is no V matrix, there is no R matrix. This statement right here is essentially equivalent to a diagonal R matrix type equals VC, where I'm saying that the residual variance is constant over occasions and persons, and there's no residual covariance. So the mixed output that I would have gotten from the empty means model written this way is right here. In mixed, it separates out the variance components from the fixed effects. NLMix just dumps all the parameters together. So NLMix output has the same fit statistics box that you see in mixed. I usually don't print this one anymore. I print the version that comes from the information criteria table that includes the number of parameters, but that's not designated output in NLMix, so I'm putting these here for comparability. As you can see, they are exactly the same. Also noted is that NLMix only comes in regular flavor maximum likelihood, so that's why it says -2 log likelihood as opposed to -2 res log likelihood. NLMix is an ML only procedure. But the 3 parameters that I listed, fixed intercept, variance of the random intercept, and variance of the level 1 residuals, are just given in one table. So this is why it's very important for you to list names that will be readily interpretable to you in trying to figure out what these estimated parameters refer to. And you can see that they are spot on with what we would have gotten from the mixed output. An additional column that you'll want to pay attention to that does not show up in mixed, it does show up in GLMix, the nonlinear mixed models package, is gradient, which is out here. So these are very tiny numbers, e to the -9, -10, meaning 9 or 10 decimal places before you hit a number. This is good. What a gradient is the first derivative of the parameter with respect to the likelihood function. The first derivative of the function with respect to the parameter. I'm saying it backwards. This is why I write these things out. So you want these values to be as small as possible because they indicate the slope at the top of where the estimate is with respect to that parameter. So this is good. So we keep outputting this column just to make sure we are watching any parameters that have difficulty converging. Even if the overall model says it's converged, it's possible for certain parameters to go haywire. So we list that there. And then last but not least, there's a separate table for any additional estimates, such as the one that I requested right here, the intraclass correlation. And this intraclass correlation would directly match what is provided in vCore in mixed. However, in doing it this way, we also get a standard error. So even for models that are possible to be estimated in mixed, occasionally I will estimate them in NLMix when I need standard errors for linear combinations of variance components. So for example, in doing genetic analyses, where we're interested in carving up variance into how much is additive due to genes, environmental, or error, all of those parameters are linear combinations of variance components, and typically people want you to report standard errors for them. So I will do those sorts of analyses using NLMix to get standard errors for linear combinations of variance components. You can also do the NM+, by the way. So upping the level of complexity then just a hair, we have a random quadratic time model. So this is what it would look like in mixed using maximum likelihood estimation, and this is what it looks like in NL mixed instead. So we have then 3 fixed effects. We have a fixed intercept, we have a fixed linear time slope, and a fixed quadratic time slope. We have 6 total parameters at level 2 in the model for the variance. We have the variance of the random intercepts. We have a covariance between the random intercept and the linear slope. We have a variance of the random linear slopes, covariance of the intercepts and quadratic slopes, covariance of the linear and quadratic slopes, variance of the quadratic slopes, and then last but not least, our friend E. So the variance of the level 1 E residuals is the last term being estimated here. So there are 10 total parameters in this model. And the start values came from what I got out of mixed. So the level 2 equations then correspond directly to what we would see in a standard random quadratic model, where I have 3 level 2 equations: the beta 0 individual intercepts, the beta 1 individual time slopes, the beta 2 individual quadratic time slopes, each of which is a combination of a fixed effect, so fixed int, fixed length, fixed quad are the 3 fixed effects I'm defining, and a random effect, an individual intercept, individual linear time slope, individual quadratic time slope. Then the level 1 model that builds pred y, or y hat you can think of, is a combination of the beta placeholders that you would typically see in the level 1 model, multiplied by the level 1 variable that they correspond to. So my intercept goes here. These are my individual linear time slopes, my individual quadratic time slopes. Then, as before, we tell it that our outcome is response time, which is conditionally normally distributed. The mean for the variable is given by the function. So the combination of fixed and random effects, that goes here as the conditional mean for each row of the data. And each row of the data has the same conditional variance, the level 1 residual variance of the e's. In the random line, now I have 3 different random effects, therefore I have to give it a 3 by 3 matrix as well as a mean vector with 3 places. So these 3 random effects, the intercept, linear slope, quadratic slope, they all have means of 0, has to be that way in these models. And then in order in which they would appear in the G matrix are the terms for the variances and covariances that I have defined up here. So the variance of the intercepts, covariance, variance of the linear time slopes, covariance, covariance, and then variance. And of course the nesting variable at the end as usual. So then this G matrix that shows up in proc mixed is what I am recreating with this statement right here. So that's how I know what order they should go in, is what order they show up in mixed. So then here's the mixed output, where we have our -2, our variance components, -2 log likelihood, and then the fixed effects. The NL mixed output looks similar. So again, we have the exact same fit statistics in each model because this is the same model, just estimated using a different routine. And then it dumps all of the parameter estimates into this one table. So the 3 fixed effects are first, and then all of the variance components are next. I believe it prints them in the order in which you list them on the parm statement, so it's good to be thoughtful about the order in which you do things so that the output is organized in a way that is helpful to you. And so all of these match exactly what we got out of proc mixed up here, and all of them appear to be estimated well. Note the gradients are all very tiny numbers. So one switch in terms of what gets estimated in the negative exponential models that are going to follow this is that rather than estimating variances directly, they are going to estimate standard deviations. This is a trick that's used in a lot of places to improve numeric stability, particularly for numbers that are very large or very small. So in this case, because our outcome is response time in milliseconds, these numbers get very big. They have very large standard errors as well. So I'm borrowing the trick of switching to estimating standard deviations instead of variances. This is the same thing that happens in LME and R, for instance. So now we get to models that are not estimated in mixed, which is the reason to do this. So just to remind you what we're going to be estimating, we're focusing on negative exponential models. So this is lecture 6, slide 37, revisiting here. The parameterization of a negative exponential model that I'm using has asymptotes, amounts, and rates, and we went over this in class, but just to review, the asymptote is the theoretical lower bound, basically of the function here, so it would be an upper bound if the function were growing, it's a lower bound in this case, and these three lines differ in their asymptotes, so they differ in where the function is headed as its sort of infinite value here on the y-axis. The amount is the total amount of change from where the function starts to where the asymptote is. You can also rephrase an amount as an intercept. So as you can see here, these three lines end up at the same place, but they differ in the total amount of change, the total distance on the y-axis that the function has to traverse over the amount of time. And then finally, the rate parameter. This is the nonlinear parameter. It's negative, meaning that the function is slowing down. So it's negative not because it's going down, but because it's slowing down. So all of these functions have the same total amount of change. They all start at the same place. They end at the same place. They have the same asymptote, but they take different amounts of time to get there. So the red line has a lower rate of change, is more gradual than, say, the blue line, which has a steeper rate of change. So the model that we're eventually going to build up to looks like this. This is slide 39, where the level 1 function is nonlinear. So we have e to the rate times time. That's what makes it nonlinear, and that's what makes it not possible to estimate in mixed as a standard multi-level model. But just like we had in any other instance, we have level 2 equations, individual parameters for each person that are a function of fixed effects in red, as well as random effects in blue. So rather than beta 0 being an intercept as usual, in this case it's an asymptote. So gamma 0, 0 will be the fixed asymptote where people end up on average. U0i will be how far off your individual asymptote is from the one that is on average. Beta 1 is going to be the amount of change, where gamma 10 is going to be the average amount. U1 is going to be the individual deviation from that average amount. And then beta 2 is the rate. So this is how fast the function approaches the asymptote on average for the fixed effect, and then individual differences. And just to foreshadow what's going to happen with U2, it's not going to be estimable. Its variance is not going to be able to be found. I've never actually gotten it to estimate in real data. So I apparently don't have enough data or enough of a difference in rate. It's unclear. So this is the model that we're eventually going to end up with, but I'm going to approach it in a stepwise fashion. That way I can get decent starting values for each layer of the model before continuing on. And I'm going to fix this underline because I am anal and it bothers me to look at it. All right, so here we go. Our first negative exponential model only has fixed effects in it. There are no random effects. So here we have 3 fixed effects and we have level 1 residual variance. So where these fixed effects came from is educated guess based on the data. So I know that in these data, the response time on average at session 6 was somewhere near 1600 milliseconds, and so I made that a starting value for the asymptote. I also know that response time on average at the beginning was about 300 milliseconds higher. So I made that the amount. So people started on average around 1900 milliseconds. They ended up around 1600 milliseconds, and that gave me the basis of these two starting values. For the fixed rate, I know it's negative because I know on average the function is slowing down as it approaches the asymptote, and I just put 1 in there just because. So not really an educated guess, just a starting value. For the standard deviation of the residual variance, this is the square root of what the residual variance is going to be, and that's based on what it was in several of the other models that we estimated for these data. So the objective of estimating this model is to get better start values for these 4 parameters before adding in any random effects that are going to cause additional estimation complexity. So we are setting up the 3-level equations the same as in the model here, but they'll only have fixed effects at this point, which is why we have just these 3 entries right here. We have a predicted value for the level 1 equation, which is a function of the asymptote, and then here I have written out the level 1 equation as it is given right here. So we have the amount times e to the rate times time. So in this case, I am using the time 1 variable. So apparently I did need to center this, and I forgot to put it in the code. My bad. But we had this in all the other examples. This was simply created as session -1. You could also do it inside the NLMix package if you wanted to. And as before, we have response time, and it is normally distributed with a predicted value given by the level 1 model, and then a residual variance written like this. So the actual parameter that's being estimated is the standard deviation of E, but its variance is what goes in here. So I had to square it for entry into the model statement. Because it's hard to keep track of these parameters, I went ahead and made myself a trail of breadcrumbs to follow. So I'm writing out estimate statements that are nothing more than relabeling these parameters so that I'll know what they mean. And I'm also going to ask it to do the work of squaring my variance, my standard deviation, so that they are printed as variances. I'm also demonstrating how to ask it for predicted values at each occasion, as well as a linear combination of fixed effects to make an intercept. So the asymptote, where people end up, plus the total amount of change that it took to get there together form the fixed intercept. So this is an alternative way of phrasing the model, is to ask it for the intercept directly and then get the amount as a linear combination. And then the predicted mean at each occasion is a function of the asymptote, the fixed asymptote, plus the amount times e to the rate times the value of the time predictor for each of these sessions. So that looks similar to what estimate statements look like in mixed. However, you have to make it do the multiplication and the addition explicitly. So they are more similar to lin-comsense data in that regard. We get a note that the absolute overall model convergence criteria was satisfied. We get our traditional fit statistics. We get the estimated parameters that we requested, and then we get all of the estimates. So these are the values that I will use as start values for the next model. So the actual fixed asymptote was estimated at 1675. That's not too far off from what I guessed here based on just the data. The amount, 284 instead of 300, and the rate was estimated at minus 0.7. So that parameter doesn't have a ready interpretation in terms of, change per units in the way that we're used to thinking about a slope, because it is a nonlinear parameter, and it will be the one that's most challenging to estimate in terms of its fixed and random effects. So it's good to have a decent starting value for that before moving forward. Then we have the squared standard deviation of the e's here, and then come the linear predictions from the fixed effects. So the fixed intercept, and then the predicted mean at each of the occasions. And note the intercept is the same thing as the predicted mean at time 0, because that is the definition of the intercept. So now I'm using these parameters, up here, these parameters that were directly estimated as start values, and I'm adding in a random asymptote. So the standard deviation of U0 is not an intercept in this model, it's an asymptote. So I am allowing individual differences in where people end up as the first random effect. So everything else is as it was before, other than better start values for the rest of the parameters. This is just an educated guess for 10 for what a random asymptote variance would be. And I have my 3 level 2 equations, picking up the random asymptote here, U0. The level 1 model looks exactly the same. The model statement looks exactly the same. And now I have a random statement added here. So I have the standard deviation is the actual parameter. I have to square it to form the variance of the U0s. And then we have the trail of breadcrumbs for our parameters, as well as asking for the squared terms that form the variances of the level 1 residual and the level 2 random asymptotes. And then also the same predicted values for the fixed effects and then the predicted mean in each occasion. So relative to the previous model, the only new term that's been added is right here. It's the variance of the random asymptotes. So I did a likelihood ratio test relative to the model with no random asymptotes and found that this is a significant improvement. So adding this U0 term, more specifically its variance right here, significantly improved model fit. That means people have different asymptotes for where they end up. So then we have the model parameters that we asked for. All the gradients look pretty good. And then these are the additional estimates that we asked for as well. Then we have model 6C. This is adding a random amount. So using the start values from our previous run, including now a better start value for what the standard deviation is of the random asymptotes, I throw those in there and I pick up 2 more. So because I already have a random asymptote, I'm adding another random variance. That means I'm also adding its random covariance with the asymptote that was already there. And these are just educated guesses again for what these parameters would be. Because all of these other ones are going to be good, it matters less what you put here. So I just put in positive values because I expect them to be positive values. So adding in a random amount right here. Otherwise, all of this code is exactly the same. The random amount is added here. So now we have a 2 by 2 G matrix, which means 2 means of 0. And then here's the parameters in the G matrix in order in which they would appear. The variance of the intercepts, the covariance of the intercepts and linear slopes, and the variance, or nope, not linear today, wrong model. The variance of the asymptotes, the covariance of the asymptotes and the amounts, and the variance of the amounts. That's what this thing is right here. And trail of breadcrumbs for all of the actual covariance terms, and I'm also asking for the correlation. So taking advantage of this ability to do math so that I can get what would have been in G-core between my 2 random effects as well. And in adding those 2 parameters, so change of 2, because I added in a covariance and a variance, that significantly improved model fit. So people need their own amounts of change in addition to their own asymptotes. Here are all the directly estimated parameters, and here are all of my estimates that I asked for from those. So at this point, then we can compute effect sizes for the random variances using confidence intervals as usual. So at this point in the model, there's 2 parameters that have both fixed and random parts, the asymptote and the amount. So I'm using the fixed effect as the middle of each of these confidence intervals, and the random effect variance that goes with it, the asymptote variance as written right here, and the amount variance as written right here. And so then this gives us the range in which 95% of our sample is expected to fall. These are predictions, not actuals, so assuming symmetric random effects and all that. But this says that at the asymptote, so asymptotic best performance is predicted to be somewhere between 827 milliseconds and about 2500 milliseconds to do this task. Whereas the total amount of change is anywhere from a negative amount, which actually means they're getting worse in this context, up to an improvement of 825 milliseconds. And this is true with the data. Some people actually did get worse over time as they got more practiced. Maybe they hated the task. That's entirely possible. And for the last model here, I am adding in a random rate. So this person right here, U2, which requires adding in 3 new parameters. And I'm trying to remember where I got these start values from, and I don't. But I think what I had tried to do is to mimic these based on something else, but the rest of them should have come from the previous run here. Clearly, I've played around with this more than I recall to make it work, but the take-home message is that no matter what I did, it doesn't work. So adding in this new random effect, more specifically adding in its 2 covariances with the random effects that are already there and its variance, we got the model to blow up. So it just said, nope, sorry. I looked at the documentation as to how to improve the convergence rate. So I tried different start values. I tried, this is a easier to estimate version. It's called first order approximation, where I was trying to make the model easier to estimate, get better start values, and it still didn't work. So I take this to mean that we don't have a random rate that is detectable in these data. So we call it good. So then, as we did with some of the other models, I'm showing you the best out of each family with respect to the mean response time at the top and then the variance in response time at the bottom. So we have the saturated means model, the black squares and the solid line. This is the answer key. So these are the maximum likelihood estimated means at each occasion. And we can see random quadratic is one contender. That's this line right here. It does a decent job, but we learned in our absolute fit comparison that it didn't fit. The piecewise model is the circle one here that looks like an elbow. That one did fit, as we learned in our comparisons of absolute fit. And now we have a new contender, the random asymptote and random amount fixed rate model, which is this one right here. And so this one looks the most reasonable in terms of what it predicts would happen if you had additional measurement occasions, but we haven't found out if it fits yet, so we'll do that next. With respect to the variances at each occasion, we have the actual model predicted variances from an unstructured model given by the black lines here and the squares. We have what is predicted by random quadratic, so that's this crazy function right here in which the variance changes across time quartically. And yes, I'm going to stand by that made-up word. It's time to the 4th power, quartically. We have the prediction from the piecewise model in the circles, in which this is a joint function of 2 different quadratically changing variances, so we see this sort of U-shaped curve. And then here's what it looks like for random asymptote, random amount. So this one does a theoretically plausible job, I will say, because it predicts that after people are done improving, that they become homogeneous, which makes sense that eventually the curves would become parallel. But as you can see, it whiffs on this section of the curve right here. So let's test those observations more formally. Here is how we're going to add in contrasts for the session-specific dummy codes. So we did this in all the other examples. Basically, we're saturating the model for the means with respect to time. This model has 3 fixed effects, an asymptote, an amount, and a rate. So we're adding 3 more. That would get us up to perfectly reproducing the 6 means. And then we're going to test whether these 3 new fixed effects are significant. So I'm adding in 3 new fixed effects as parameters, putting them into the level 1 equation here, and then adding a contrast statement. So this is similar to the contrast statements we used in the mixed examples, except that you have to make the multiplication explicit and the commas delineate different numerator degrees of freedom. So the question is, did adding in these session-specific dummy codes help? If so, then the model doesn't fit. And survey says it did not help. So what that tells us is that the curve predicted by the random asymptote random amount model, the star looking things here, that did accurately capture these 6 means. Doesn't look like it's going to do a good job on the variances side, so let's check that out. What I decided to do is compare the fit of this model that has saturated means, given the 3 new parameters that make it saturated, against the saturated means unstructured model in mixed. And it looks like, as we suspected, there is a significant improvement in model fit from adding in unstructured. So the random asymptote and random amount do not do a good enough job in reproducing the pattern of variance and covariance across time. So the comparison is somewhat unfair because all of the other models that we tried had 3 random effects, whereas this one only has 2, but it doesn't do a good enough job. So example 6b. Isn't it amazing how you can only see typos when you're giving a lecture? And that's the end of the story. So where I would head next, so the fact that you have to estimate this nonlinear model in this much more laborious framework can be off-putting. The fact that this NLMix estimator does not have REML and does not have denominator degrees of freedom options is problematic for small samples. And so that was the basis then of moving to an approximation using log transform time instead. And so this is a tactic by which you can use a standard linear model, slope times variable plus slope times variable, and you can use a standard mixed or SEM package to do it, and yet you can recreate curves that look exponential-like. So for instance, this red line here does a pretty good job of approximating an exponential using a linear effect of log transform time as well as a quadratic effect of log transform time. So example 6D that we went over at the end of the last class then fits these models in mixed and determines that for our example data, it actually did fit adequately. So that is going in my next revision to the book because I think that that's a useful thing to know. All right, that's it for now. Hope to see everybody later this week. Thanks for watching.